Welcome to our introduction to distance vector routing. In this video, we will explore how routers use this technique to share information with their neighbors, calculate the shortest path destination, and ensure efficient data transmission across networks. We will also look at popular protocols like RIP, discuss the benefit of this approach, and cover some of the challenges and solutions that come with the using distance vector routing. Let's dive into the basics and understand why it remains a fundamental method in networking. Distance vector routing is a key technique in dynamic routing, helping routers decide the best path for data to travel across a network. In this method, each router shares its routing table with nearby routers at regular times. The distance refers to how many routers or hops are between the source and destination, and the vector is the direction or next router to send the data. Routers calculate the shortest path by comparing the hop count from their neighbors. An example of distance vector routing in action is the Routing Information Protocol. Simply it is called a RIP, which is often used in smaller networks. However, RIP has a limitation of only supporting up to 15 POPs, making it less ideal for large networks. While simple to use, distance vector routing has some challenges. For instance, it can take longer for routers to update paths when the network changes. It's also prone to routing loops, where data gets stuck moving between routers. To solve these issues, methods like split, partition, and hold up timers are used. Despite these drawbacks, distance vector routing is still a useful and effective method for managing paths in smaller networks. Some of the key characteristics of distance vector routings are distance metrics. Distance vector routing protocol use a metric to determine the cost of reaching a destination. The most common metric is the number of hops, the count of intermediate routers between the source and destination. Other metrics can include delay, bandwidth, or a combination of factors. Each router maintains a table is called routing table that contains the distance to every destination network and the next hop to reach that destination. Second one is periodic updates. Distance vector routing protocols periodically exchange routing tables with their neighbors. For example, routing information protocol typically updates its routes every 30 seconds. When a router receives an update from a neighbor, it recalculates its routing table and propagates the updated information to its neighbors. This process helps the network adjust to changes in topology. Third one is Bellman mode algorithm. The Bellman mode algorithm is used by distance vector routing protocols to compute the shortest path from a source to destination in the network. It works by iteratively relaxing the edges, updating the shortest path estimate until convergence. The algorithm ensures that the shortest path is found, but convergence can be slow. The protocol must run several iterations and ensure that all routers have consistent information. These characteristics define the operational behavior of the distance vector routing protocols and influence their performance and suitability for different network environments. In this section, let us discuss about pros and cons of distance vector routing. Starting with the advantages, simplicity, distance vector routing algorithm like routing information protocol are relatively straightforward. They use a single metric to determine the first path, making them easy to understand and implement. Low maintenance. Because of their simplicity, distance vector routing protocols often require less administrative overhead. They automatically handle router updates and do not need complex configuration. In the aspect of dynamic updates, distance vector routing protocols dynamically adjust to changes in the network. They propagate updates periodically or when changes are detected, which helps in adapting to a network topology changes without manual intervention. Now, let us look at the drawbacks. Slow convergence. Distance vector protocols can be slow to converge, especially in large networks or when there are significant changes in the network topology. This can result in periods where routing tables are inconsistent, potentially leading to network inefficiencies or outages. Scalability is used. These protocols do not scale well to large networks. As the network grows, the distance vector updates can become large and frequent, leading to increased overhead and slower performance. Distance vector routing protocols are prone to routing loops, where packets may circulate endlessly in the network. Mechanisms like split cohesion, route poisoning, and hold-on timers are used to mitigate this issue, but they do not eliminate the risk. Distance vector routing is well suited for specific applications due to its characteristics. Here is a brief overview of where it is commonly used. So the first one, small to medium-sized networks. It is ideal for networks with fewer routers where the simplicity and periodic updates are manageable. The overhead and slow convergence are less problematic in smaller networks. In internal routing within autonomous system, it is often used for internal routing within a single organization or autonomous system where it is straightforward nature is beneficial for managing internal traffic. Distance vector routing protocols like RIP have been widely used in older networks and legacy systems, reflecting their foundational role in networking. In case of educational networks, it is commonly used in academic settings for teaching networking concepts due to its simplicity and easy of understanding, helping students grasp the basics of routing. Distance vector routing protocol can serve as a backup routing protocol in environments where more complex protocol like the OSPF, EAGRP is used as the primary, providing a fallback option if needed. These applications leverage distance vector routing is simplicity and easy of use, though they may not be suitable for larger or more complex networks due to its limitations. The distance vector algorithm operates by having routers periodically share their routing tables with the neighboring routers and then update their routing tables based on the information received. Here is a step-by-step breakdown of how the distance vector algorithm works, covering initialization, sharing, updating, and convergence. Each router initializes its routing table with direct neighbors, other destinations. The distance to each directly connected router is set to the cost of the direct link, usually one half or the actual link cost. The next half for this distance is the direct neighbor itself. Other destination, the distance to all other destinations is initially set to infinity or a very large value, and the next hop is undefined. Each router periodically shares its routing table with its directly connected neighbors. This table includes periodic updates, distance vector updates. The table lists distance to all known distance destinations and the corresponding next hop to reach those destinations. These messages are sent to neighbors to keep them informed of the router's current view of the network. When a router receives a distance vector update from a neighbor, it needs to process the information to update its routing table. It includes calculate new distances, and a distance vector update for each destination listed in the received update. The router calculates new distance to the destination as the sum of the distance to the neighbor and the distance advertised by the neighbor. After calculating new distance, the router compares newly calculated distance with the current known distance to the destination. If the new distance is shorter, the router updates its routing table with this new distance and sets the next hop to the neighbor from which the update was received. After updating its table, the router will propagate the updated routing information to its neighbor in the next periodic updates. Thank you for watching.